good evening, good morning, or good day to everyone, depending on where you are. My name is Victor Zamaroev, and I'm engineering manager at Grammarly, and I'm responsible for a few of our NLP research ML projects here in Kyiv office, in Ukraine office. And I'm really glad that you're here, and I'm excited and looking forward to our talk today. So we'll be talking today about large language models that almost ready to pass Turing tests. So we're looking forward to that moment when we'll be able to communicate with our computers and hesitate whether it's computer or human in front of us. So hopefully this will be soon. And today we'll talk about what does it mean for us in this era of giant language models to do on edge devices, how we run such huge models directly on mobile devices. So we'll be having this talk today, and please submit all your questions to Q&A tool, not in the chat. So there is a Q&A button in Zoom. Please submit all the questions there, and we'll answer all of them after the talk during the Q&A session. If some questions won't be answered, we'll definitely make sure that we answer them during the networking session right after this meeting. So we'll be having a networking session after the talk, and we will post all the links to your room directly in the chat. Also, I want to take a moment and invite you to our upcoming machine learning and research events. The closest one will take place next week on February 2nd, and we'll talk about how we can help our users to communicate with confidence, and we'll discuss in details about 3 different projects that we do in Grammarly from 3 different speakers. So you'll have a chance to know a bit more and learn about machine learning in Grammarly. And also one of our speakers, Tushar, will describe how we run our models directly on mobile for recent Samsung launch and integration with Samsung. So that would be really interesting for anyone who's interested in this topic. And also there will be a second talk on the week following the next one. So on February 8th, we'll be holding our new researchers from Japan with whom we collaborate to introduce a new shared task, how to automate feedback comments generation for language learners. So at Grammarly, if you're using Grammarly, you know that we show a lot of suggestions, and we do explain them to our users, like what exactly this suggestion mean, like why do we think that we need to fix this mistake, and why do we think that it's actually a mistake. And we'll talk about how we can automate this kind of feedback that we generate to users without like using rules or our expert knowledge, but using pure machine learning approach. With that, I'd love to introduce Max, who recently joined Grammarly as Director of Intelligence. And Max, over to you. So looking forward for your talk.
Thank you, Victor. The topic of the talk, as Victor already mentioned, this is natural language processing on edge devices. Edge devices are usually mobile devices and other devices, sometimes connected, sometimes not connected to the cloud, in the era of giant pre-trained language models. So Victor already introduced me. I'm a Director of Engineering here at Grammarly. I'm really excited. I joined this company 3 months ago. Before that, I spent 9 years at Google Research, where I worked on natural language understanding and many projects. I led some development in the area of natural language understanding on device. If you have Android phones, some features of language processing come from my team. So therefore, sorry, some of my slides would be a bit biased to work that was done by Google and by my team at Google. Brief overview of the presentation. I will say a few words about this new era of large models. I will talk about why on-device is important. We will quickly overview ways how we can bring large models on device, and then we will zoom out and look at the big picture of NLU nowadays at the end of this presentation. The era of large models. If you don't live under the rock, you definitely have seen these announcements about building bigger and bigger models. It happens like, I think that every week we get news about new bigger models created by some company. Usually this is leading big tech companies. What is so exciting? Why people are so excited about this? If you move back 3 years, close to 3 years, you would see news about GPT-2, and everybody was excited about this small story about unicorns. I put a screenshot of this story here that was published as a part of announcement of this model. People were excited about because of different reasons. Obviously, journalists and media was excited because these are people who generate text, and when they see that something else can generate text of this quality, they were excited. For me, as a person who spent about 30 years of my life in the area of natural language understanding, I think that it was also exciting because it was before all text generation was practically string concatenation. Before these large models, we didn't see any technique that can generate text of this quality and of this variety and of this imagination inside this text. Usually before, text was very engineered creation. So this is first exciting thing. We don't have any other technologies that can generate text of this quality, this variety now. Another thing is, historically, when we build any natural language understanding model, any natural understanding system, we usually spend some time on training. Usually all weights need to be trained and adjust to solve any task. It's not how people do, right? If I ask somebody to perform some task, we usually don't retrain this person from scratch, right? What happened with these large models is that we can switch to another mode of solving tasks when we don't retrain this model, but we practically provide additional information in the input. We say something like translate from Ukrainian to English, then we provide a phrase, and then the translation happens. So this new technique, which is called prompting, which is related to few-shot learning, is something new. This prompting can be by, as I said, by providing additional words. And another more common, more advanced approach, we can use this prompting by specially adjusting input embeddings of input sequence. So this is a big change how the models are designed from this point of view, that if we don't retrain these models, we just provide additional information to solve another task. Another big difference, this on the right, you can see, unfortunately not great screenshot from recent Google AI blog about the system that can chat with the user about animals. If we wanted to develop the system 5 years ago, it would be multiple systems. It would be one classifier of user intent. It would be a reinforced learning system that tracks state of the dialect. That would be separate retrieval system. It would be a lot of over-engineering, and all this stuff would be really hard to put together. This specific system is just Lambda, large language model, that is specially fine-tuned and has access to special retrieval system. So it's from engineering point of view, from development point of view, it's much simpler approach. It doesn't have a lot of components. So this large models is completely different approach how we build large systems that understand language. We just have this large model, we just fine tune it, we just attach to this model external components that are controlled by this model, not very engineered things that is based on logic and on complex algorithms. Yeah, so these are all exciting things. These are completely new approaches, and not surprisingly, many research teams around the world try to build these models. You see that it started somewhere like in 2018 when like Elmo was practically the first paper where people said, oh, we actually successfully had something pre-trained that can be used to build better natural language understanding systems. And then in 2019, there was this explosion of new models. And you can see that both scales on this graph are logarithmics. You can see that this is practically exponential growth of size of these models. And by the way, models on this graph are only announced models. I know that some companies internally have bigger models that are not announced and that are not available for usage for external users. And also it includes only classical dense models. There are also classes of not dense models that currently have trillions of parameters, but I will talk about them a bit, but this is not on this graph, right? So you can see this exponential growth of capacity of these models, number of parameters in these models. Why it has happened in 2018 and the end of 2018? The reasons are typical for any industry, right? Like first, we have new powerful hardware. Many people remember how like 13 years ago, I think, there was this deep learning explosion started. And it started by people switching from CPU to GPU, and it changed how many floats we can multiply in every second. And people started using algorithms that was not possible before. I think that about 5 years ago, we see this quick introduction of special hardware accelerators. It can be TPUs, if this is Google, and other companies also provide. Cerebras is another example of startup that builds these huge accelerators. They are much more powerful. It's practically, they surpass on the specific tasks of neural network inference. They significantly surpass any supercomputers that were built before. The second big development that happened in the same year, by the way, was change in the architecture, change in the approach to architectures. Natural language processing, because I think that people were very preconditioned that text is a sequence. Different types of recurrent neural networks was the main approach how to process text. And recurrent neural networks, unfortunately, not very scalable if you train really large models. Transformers completely changed this. Transformers is the architecture that is not only very powerful, but it's also relatively with this number of parameters, is relatively fast in training on this new powerful hardware. So transformers were this opening new architecture that made possible to build these huge models, and practically we don't have any limit on how many layers and how big these transformers can be. And the last but not least is available data. Yeah, internet and other resources with text was available for many years. But I think that during the last decade of this century, first of all, we created this very nicely prepared different collections, which covers practically all human knowledge. This is the first. The second, these are collections of different type, right? From pure knowledge of Wikipedia to fantastic literature that we can get from different collections of artwork on the internet, and ending with social chat on Reddit, right? So we have all these different kinds of natural text, and also we have technologies to effectively process it, filter, stream it into training. So combination of these three things made possible this breakthrough in large language models. Now let's look inside, like when there is a research team and it works on something, why suddenly large language models became so interesting and attractive. There is this famous blog post from Rich Sutton, and Rich Sutton is one of the founders of the direction of reinforcement learning and machine learning. And practically what he said in this blog post is that if you look at the history of all artificial intelligence, the most successful approaches historically are like saying very simply, forget about everything, just multiply numbers. So everything what leverages computation always wins in this long run of building more intellectual machines, right? So surprisingly, large language models are easy path. It's only like one architecture with a small number of variances. We just scale them up, we're just building them bigger and bigger. If you want to generate bigger text, we don't need to think about linguistics or do anything other complex. We just need to build bigger model and it will generate bigger text. The second breakthrough in training of large language models that happened also a few years ago is understanding that if you have really large model with the right architecture, it's easier to train it. It's a bit counterintuitive because we usually think that, okay, if you have very small number of parameters, it's easier to train. But it turns out that what is happening is that this is true for very small models. Then we're in some kind of gray zone. But if you have like a really, really big model with a lot of connections in this very complex hyperspace of billions of parameters, our loss surface where we optimize, where our optimizer moves to the optimum is actually much simpler for optimizer to navigate through. There is like it's much more smooth. I can say that I don't believe that currently we have a good theoretical and mathematical understanding why it happens, and theory here is a bit hand-wavy, but this is practical experience. If you can train this model, usually like it converges in really good minimum, and it's really robust convergence. So it's surprisingly large language model is easier to train than reasonably small model on the same task. Now I want to switch to second part of this conversation. Second thing that is happening is what is on device and why on device is important to move forward and to explain why we need to bring these large models on device. So I've talked about this accelerators, about the supercomputers, and when I started learning programming, the computer that we used was like size of, I think that size of the room which I'm currently in, and obviously these large computers, these data centers that we put in, where we put all our cloud logic. Actually, these are huge data centers, size of a huge mall or something like that. And if we summarize all computational capabilities of all data centers, of all cloud on the earth, it won't actually surpass summary of computational abilities of mobile phones, because we have much more of them. Mobile is the most widespread computational platform on this planet. Every other person has a smartphone in their pocket. So it's the most powerful devices that are available everywhere. This is first. Second, people nowadays, and this is, by the way, consequence of the first thing, right? Because everybody has this phone, and this phone has very private, important for us information, privacy requirements, and our expectations how these requirements can be achieved are much stricter nowadays than it used to be before. If we do communication, we do end-to-end encrypted communication. If we do search, we don't want our queries to be populated anywhere, right? So the only one way how we can protect our data, theoretically, is to leave this data on device. If our data with encryption, with federated learning, with any other approach is deployed to the cloud, now it's only a question of probabilities, because like all these algorithms, they don't have 100% guarantee. So stricter privacy requirements actually, they push more and more processing of data on device. Another point why on-device NLU becomes more and more important is because our natural language understanding technologies, the technologies of large language models that I mentioned and technologies that I will talk about, they developed significantly last years. And we can build really useful applications that can run on device. We can build applications that runs completely on device, they don't send any information outside of this device, and they can translate from language to language. They can suggest you smart reply to or completions to make your conversation more effective. They can fix your grammar, spelling, whatever. So we really can put a lot of stuff on device. If we think from what on device means, if you're a developer of a system, if you develop your own system that you want to deploy to billions of people, then eventually you'll see that big part of price and investment into building this application would be to pay for the cloud, right? Because if you build something that is cloud-based, for every request, you need practically to pay for the cloud resource. If you delegate this payment to the computational resource that is owned by your users, you obviously save money, right? So obviously you can build bigger application with less money, right? So this is another advantage of using on device. And one more thing that I think that more and more important nowadays is that if you want to build anything in the cloud, you're always under control of big tech, right? You're under control practically of 3-4 biggest companies that control the whole like internet cloud infrastructure. The only one way how you can build something alternative is to build this thing on device. Now let's do some back envelope estimation if you can run a large language model on a modern device. I think that before running it on a modern device, can we if currently this model is running on this fantastic TPU server with water cooling and with kilowatts of power, can it be fit into something smaller? Like, philosophical answer is definitely yes. Everybody whom you know has a device that can run a large language model on them, right? So our brain weighs about 3 pounds, 1.3 kilograms on average, I think, and it has power envelope about 20 watts, and it can generate pretty good natural language text. So yeah, so at least with some technologies, this is possible. Is it possible with our current technology that we use in our mobile phones? Let's consider, I don't know, it's about like Pixel 6 modern phone from Google, right? Pixel 6 phone. Okay, so 8 gigabytes of memory. Oh, formatting is not right. So this is 10 to the power 10 flops of like, this is what TPU can. This is how many float multiplications can be done on this device, 10 to the power of 10. And let's try to think if we can fit the relatively modest by nowadays size of GPT-2 model with 1.7 billion parameters. Memory. Okay, this phone has like 8 gigabytes. Every parameter is 4 bytes plus some other structure, so it would be about 7.5 gigabytes. Okay, it can fit. Latency. So Obviously, if you want to do one step of inference, if you want to predict next word, let's forget about caching for a second because it doesn't save us order of magnitude. But again, we're doing very high level estimation. So we need to multiply every weight at least once, right? Because this is a dense model. Every weight needs to be multiplied at least once to do one step of inference. Right, and it turns out that, okay, it looks like we need about 200 milliseconds per word or word piece, whatever we use for our tokenization. So it would take like, I don't know, up to 2 seconds per phrase. I think that it would be very strange if you communicate with somebody and everybody does like 2-3 seconds pause before replying. But it looks like, okay, it's feasible. We're already there. What the problem is? Unfortunately not. Every edge device does a lot of things. If you compare it to a cloud server that can be 100% allocated to serving very specific problem, your phone in your pocket at this moment of time does a lot of things. It communicates to the cellular network. It has some internal stuff that is happening. So all operating systems that are running on these devices, Android, iOS, and a few other, they always limit size of these applications and they try to push them out of memory because memory is very limited resource. So on this slide, it's not a real graph. Real graph is much more noisy. I will talk about it in a second. But imagine that we started like from even smaller, 100 million parameters model, and we reduce size of this model and we run inference and we look at latency. And surprisingly, you can't really allocate 100 megabytes on Android phone. What would happen is that it would swap this data, right? So memory will go to the storage, to this bigger storage that the device has. And on the modern phone, even with modern interfaces like UFC 3.1 and so on and so forth, it's still only a few megabytes per second throughput. So at this regime, where operating system just pushes your model from out of memory, you will see that the speed is relatively low and it's independent from CPU and TPU because it's practically, and by the way, this is logarithmic scale again, it is dominated by input-output latency on your phone. And then you would see like this significant drop. It means that, okay, finally we completely in memory. But you can see that it also scales relatively slow and difference between CPU and TPU is not so great. What is happening here is that you read weights from memory, and memory on mobile devices, even if this is DDR5, it's still much slower than on big computers. And also, it actually uses a lot of battery, but this is a bit different problem. Then you will see that because TPUs usually have, or any accelerators, I don't know, from Samsung, they have their own accelerator, from Qualcomm. They have some bigger cache, usually a few hundreds megabytes of memory. You can see this like significant drop of latency, and then the same drop you can see on CPU. But it's much slower than we expected, right? So because of all these limitations on how fast parameters can be propagated, actually our mobile device is more limited by the speed, how we can load parameters into our processing unit, not by how fast this unit can multiply numbers. Another problem, why I said that if you try to build it in reality, this graph would be much worse, is that many edge devices are not great with thermal control, right? They don't have fans, they don't have water cooling. Of course, if you're a fan of mobile games, you might attach fan, and even I've seen even water cooling to your phone, but in reality, it's not happening. And what these devices do, they do what is called thermal throttling. So if you run your model and you run, for example, one inference for the first word, and it's nice, it's 200 milliseconds. Suddenly, the second word is 1 second. What has happened? The phone did like a lot of multiplications, the temperature went up, the governor of the hardware, like this part of operating system that controls hardware. It looks like we are going into this overheating mode. Let's reduce our speed. Let's reduce CPU clock like 5 times. And you're screwed, right? So it's as slow as molasses, and you cannot do anything. The second problem is more like engineering problem for a developer. It's practically, I mentioned that there is iOS and there is this metal accelerators from Apple, there is Android, and Android you have multiple different accelerators starting from TPU accelerator on the Tensor chip from Google and Samsung, Qualcomm, and all other companies provide different, and they all have different strong and weak points. They have all different architecture, so it's a lot of problems to optimize. And because this naive approach doesn't work, we need to introduce some optimization procedure. So in large picture is that we have this model. It's usually large model, or it might be many models. Many systems use ensemble of models to improve quality. Then we have some optimization procedure. This optimization procedure can use or can sometimes it doesn't need, but usually it needs some training data. This is maybe the same training data that was used for training large models. It could be training data depending on task that you want to run on device. And as a result, this optimization procedure provides creates on-device optimized model that has either the same quality as this input models, or usually we have some drop in quality, but for practical reasons, it's often not significant. What this procedure does, what is the main intuition inside this procedure? The intuition here is that these large models are fantastically redundant, and we can try to squeeze them into something small. Why we think that they're redundant? If you have our model with that, like we can say, okay, this is our model, and it has all knowledge of Wikipedia, and we want on our phone build a fantastic system where we can talk about every topic about Wikipedia, and it would answer us, right? So Wikipedia dump is about 1 gigabyte of memory, actually, if you compress it and if you remove history of changes, right? And our model is like 8 gigabytes, as we saw before. Or in reality, these very large models like GPT-3, right, it would be like hundreds. So there are a lot of redundancy, and we can somehow remove this redundancy. And there are like a few ideas how to do it, and we will look into it. And the first one is distill out knowledge. What does it mean, distill out knowledge? The first paper about extracting main knowledge, that there is like all this noise inside the model, but there is some deeply like knowledge that we really need, and we try to extract, is by our modern standards of quickly developing area of deep learning is very old. This is paper from 2015. By the way, when you get my presentation, all these images, there are like 2 types of images. Some of them have links, like this image, for example, has link to the paper, and you can learn the paper. If you have an image without any link, it means that I created it. This is part of this presentation. But my point was that you always can read these papers. So the idea was, okay, if you have a large model, and we know that large models are easy to train and all the advantages, you can then use the output as training data to train smaller student model. And there is no good theoretical explanation how it works. Originally, people thought that this knowledge distillation works well because it smoothes output labels the right way. Now, I think that people don't think this way. They also think about other reasons why it works. But it turns out that it works. You can really create smaller model by training not on real labels, but labels that are produced by the teacher. But when people try to stretch this approach and they use bigger and bigger teachers, And at the same time, they wanted to create smaller and smaller students to eventually deploy them on device. It turns out that distillation breaks. It's really hard to find what usually researchers and engineers call distillation recipe to effectively train the small models. And the idea was try to provide more information from the teacher to the student, right? So this is classical knowledge distillation. And here we have information from teacher comes only through labels. And I think that this is, sorry, that's wrong English, should be mobile bird. But the idea in mobile bird paper, that was one of the first where this thing was published, is we use teacher, but we provide more information from internal levels. For example, we can take layer 10 of our huge teacher, and we can say, by the way, embeddings at layer 10 need to be close to embeddings from the layer 1 of our smaller student. And we can do them from layer, for example, 20 to layer 2, and so on and so forth, right? So we can compress model up to, in practice, up to 100 times. But by providing this additional information, we can train models with much, much different size. And there are all combinations, like currently there are many papers on different combinations of these ideas. Another approach that people do, they, for example, build the student step by step by providing information in different layers, or they, for example, train first smaller student, then use the student as teacher to train a smaller model, and so on and so forth. So there are many ideas how we can remove this gap, and we can really use distillation to generate a model that may be current state of the art, like up to 100 times smaller than the input model. The second idea, okay, so why don't we, during training, somehow label these weights that are redundant and force the model to remove this redundant weights from the model? And this is idea about specification and pruning. Obviously, if a weight is 0, it means that we effectively removed it, because multiplication by 0 is null. It doesn't do anything, right? But if we try to specify, and if we use something like L1 regularization that forces some weights to 0, we will have this result weight matrix that is looks like sparse, but it's random. It can be only 10% of non-zero weights, but they just like distributed like this. And our modern hardware that can stream and multiply multiple numbers, billions of floats, it doesn't work well when you're saying, by the way, multiply number 1, then you jump to number 100, then to the number 113, and so on and so forth. So these jumps are very, very ineffective. So what we need to do, we need to have some structural specification and pruning that create matrices with some structure where we can easily skip big blocks with predictive structure. And this is images from this Big Bird paper when what they do, they practically introduce this artificial sparsity into attention matrix, and then they can specify. Another thing that, because we know that training is noisy and that the model has redundant data, maybe we just don't need to keep the whole precision. Maybe what we have, we use 4 bytes to save every float. Why don't we use 1 byte or even less? Why don't we use 4 bits, right? This is approach that is used quantization, and it works fantastically well. There are 2 known ways how to quantize. One is called post-train quantization, where we just take our trained model and we practically convert all weights into smaller precision. The one problem is we need to save the same ranges, because when we go to a nonlinear function, we need to save the same behavior. We cannot move into input range of nonlinear function. So this is what calibration does. Sometimes most of models really survive this procedure really well. Some models are sensitive for it. For example, transformers are usually very robust to quantization. Recurrent networks are not robust for quantization. In this case, we use a special training that takes into account this additional quantization noise. So quantization can save us, like it can reduce size of the model 4 times if you switch to 1 byte. For natural language understanding, I haven't seen any success with lower precision. Unfortunately, it doesn't really increase speed because we still have the same number of multiplications. Okay, so we just worked on our model as this. We just tried to use the same architecture, but smaller model, maybe specified, remove some ways, but the same model. Maybe what is happening is that we are using not optimal architecture. Maybe transformers work for large models, right? All this like naive story about larger scale. But maybe there are other architectures that really work well on these smaller models. For example, for every model, we have this huge embedding matrix for every token. And if we try to classify languages and we want token for every language, it would be billions of tokens input vocabulary, and it would be huge embedding table as the input. So there are all these ideas, and it was, I would say, cottage industry a few years ago to create this very custom model architectures, and they, by the way, was usually used as students. For example, you can completely drop embeddings by using random projections and then bottleneck layer. You can completely remove transformers using convolutional network. And you can really increase speed of your model and can significantly reduce size of this model by using all these tricks. But you need a lot of engineering, a lot of understanding how these models work to invent them. And another thing that I think that nobody has resolved so far is that we can really build very small and very fast models. In the example that I mentioned, there is an open source model that does this random projection tree, and it classifies 100 languages with very high precision, with the size of the model only a few kilobytes. But there is no really such developed models with all these tricks that can, for example, solve more complex tasks. And I will talk what more complex means soon, but practically it turns out that it's really hard to design effective architecture, but this architecture can also solve a lot of different tasks. Advantage of large language models that we can easily switch and do multitask learning and prediction. Okay, so if this is so hard, if we need a person who has a very good understanding of how models work to invent this effective architecture, and we know that usually if you have some problem, computers are better in solving any problem that we know, if you can formulate this problem that human can do. Why don't we use machines to find optimal architecture? So why don't we use what this architectural search approach or neural architecture search approach to optimize, to find structure that is most optimal for this kind of inference that we can do. And you can see there are a lot of papers from this. This is a very hot topic right now. And it can reduce size of the model significantly, and even more than that, it can improve speed of the model significantly, and it can even increase quality of the model significantly. One obvious disadvantage, but for somebody advantage, but something that people are not comfortable with. This is an image from this paper about evolved transformers. On the left, you see like classical transformer encoder block. And on the right, you see what was produced by this architecture search. And you can see these models look like something that is very hard to understand. But it works. Again, like this is, for example, post and on Google Research blog. This is kind of work that it really runs on in your pocket on your device. Really, this approach. Now let's think about what's inside our model. Maybe we can remove something from our model, or maybe we can somehow change how we store weights in our model such a way that we can reduce its size significantly. Let's think that let's think about model. What's inside our model? So it has obviously knowledge about language, right? It knows grammar, something about structure, how sentences are formulated, right? So there is this common knowledge about language, and some weights inside this model are in charge of this. They know about language. But also, if you play with any model, if you play with GPT-3, if you play with Lambda, and you ask something like, which planet is closest to the sun, right? And it replies properly to this question and provides correct output to this prompt, means that it also has knowledge about the world. It's really hard to separate them. What is knowledge about language, what is knowledge about world, because like all these things are so mixed. But maybe we can remove a lot of this knowledge about world when humans solve any problem. And this is a picture from Wikipedia, but this is typical story about how psychologists and people who think about brain sees how our brain works. If I'm doing this presentation, a lot of parts of my knowledge that I have about, I don't know, about my family, or about, I don't know, that I studied Chinese language, like everything, all this part is gone. I have like relatively limited amount of memory that is needed to solve this task. I don't multiply all floats on my weights in my brain. I don't run through all my memories every time when I want to generate next word when I'm talking to you, right? So maybe we can split memory into pieces in this model, and in this case, we can reduce the number of multiplications and the amount of information that we need to process. And yes, it works. The most popular approach right now is completely automatic. People don't really explicitly split into different types of memory, but they split it into experts. This is called mixture of experts approach. And it can reduce number of models, number of parameters in this model significantly. So, but it reduces only number of parameters that are multiplied. How it works? We have what are called like routers. These are parts of the model that takes, for example, input embedding, and it says, oh, based on this embedding, I want to use expert 1. Or based on this embedding, I want to use expert 2. And by the way, the biggest models that we currently have with trillions of parameters, when I had this slide with current large models, I said that it's only dense models, because this, based on experts models, they are like orders of magnitude bigger, but they use, during inference, for example, they use only 1% of parameters for every inference. This is how they can be such huge models, and at the same time so fast models that we don't wait minutes for the production from this model, and they can be trained relatively fast. So currently, again, like, sorry, the presentation was updated to have like better design, and all powers are like in 10 to the 12 power to 10 to the 14 power, so trillions of parameters. So at this scale, it works well. I personally tried, and many other people tried to really bring it to scale where it can run on each device. Unfortunately, no success yet. We don't know how to bring this mixture of experts model on device and how to use this idea to run something on device. Another approach that is more recent, and I think that it has chance, and maybe with a very high probability you will see something based on this architecture on your device. This is based on retrieval. And how it works is that you have explicit retrieval data set, right? So you take some training data, some big set of training data. I don't know, if you want to build a system that, again, answers questions about Wikipedia, talks about Wikipedia, you can take all text of Wikipedia and some additional text. Or if you build a system that can chat with people and help them to solve issues with some system, you take all documentation from this system, right? And you put it as text. And what the model does, it looks at the input and it retrieves relevant neighbors to the input, right? It retrieves relevant documents. And then when it generates result, it uses this input additional data that is retrieved from memory to generate output. And this is relatively popular recent publication from DeepMind. They built a model that is 100 times smaller than the large dense model. And at the same time, it has the same quality on all tasks where they verified it. So yeah, so it works. This model, by the way, is called retro, right? Yeah, so it works, and I think that there is a high probability that you will see this kind of architecture on your device pretty soon. So we covered many ways, and there are a few other, and there are many other topics that I don't have time to. We have 10 minutes left. I don't have to dive in, right? So I mentioned that we have multiple architectures, but we also have multiple frameworks. We haven't touched how text is represented as input and output from these models, and there are many things around what we can do here to improve our models and speed of processing. I haven't touched topic of multilingual models, and this is another big story, that these large language models, they not only support one language, but they can support multiple languages. And interesting fact is that especially for low resource languages, you can get much higher quality of your model by mixing these languages together. I haven't talked about multimodality. This is another, I think, that kind of breakthrough. When people use language, people have different modalities. We have vision, we have our hearing, right? We have sound. So we mix words because they sound the same. When I say something like early morning, I see this picture of rising sun, right? So all these things actually, they work together with language, and maybe we can improve language processing by multimodality. And on the phone or on mobile device, multimodality is even more important because we have cameras, we have microphones and other things. I won't go there, but this is also an interesting topic. Another topic is, if you're a developer, you might be afraid to put your model on device, simply because now it is not controlled by you. Somebody has unlimited bandwidth and can extract, for example, some knowledge from your model or can reproduce your model, and there are ways how to fight it, but I won't talk about it. And there are many other topics about on-device that are very interesting, but unfortunately we don't have time. Next time. Now, let's a bit zoom out, and let's a bit think about natural language understanding, where large language models in this large picture of natural language understanding, and where natural language understanding on device is, and what we try to do when we work on all these topics of natural language understanding on device. To start this conversation, I want to introduce some framework, how we can talk about what is easy, what is hard in natural language understanding, when we need a small model, large model, how can we even reason about it, right? And I want to introduce this idea of task complexity, right? When we talk about model complexity, this is always correlated with number of parameters. But task complexity is harder to understand. Let's think about task complexity as complexity of the output space. If you do classification, if you classify text into spam and ham, right, not spam, then independently how big your text is, how complex your text is, in how many languages this text is, you have only two classes. Your output space is very simple. It's only two classes. So these are like classification is, from this point of view, is very simple task. Of course, it can be multitask classification. For example, if you do sentiment analysis and I will put 3 ratings like negative, neutral, positive, it's a bit more complex, but it's still always limited size of the space independently of size of the input. More complex thing if our output space linearly depends on input sequence length, right? So if we do sequence labeling, practically our output just depends on how long our input text is. So it's a bit more complex now. Like our output space actually is growing. If you do something like parsing, if you build trees on top of our sequences or any other complex labeling, which is not trivial, we are moving into exponential spaces where there are exponential number of solutions. Then, starting from sequence to sequence, surprisingly, we're moving into infinite spaces where like any production, any stream is possible output from our model. But in sequence to sequence, we have strong supervision. Our input sequence actually defines output. So this is, it limits it. If we do something like this example from GPT-2 free text generation, this is the most complex task because now we don't have, our space is unlimited as it was into sequence to sequence, and it's not regularized. So this space doesn't have any strong structure that is enforced somehow by input, right? So this is our idea about task complexity. So what's happening with our models? Obviously, there is a theoretical limit. If you want to predict only two classes, we need at least one integer, right? We need to be less than zero, up than zero, right? So for easy tasks, we need less parameters. As we grow up, as we solve more and more, there is some theoretical limit. And at some level of time, at some level, we need more and more understanding of language. So we need bigger and bigger model capacity. If we talk about models that I mentioned, what is happening is that these custom optimized architectures, really small models nowadays is like kilobytes models, they can unfortunately solve only very simple problems. As we advance our architectures, we can see that we can solve more and more complex problems. And now we have these large models that practically goes into exponential boost, exponential ascent of size. And this is bandwagon. This is what everybody does. So on-device NLU is an interesting story. We're trying to get from here and move as close as possible to the theoretical limit, build this as optimal as possible model that can be still useful for people. Let's wrap up, talk about summary, what we can do on device. I want to say that with our current hardware, tasks up to sequence are common, and this is a solved problem. Industry is already there. You can see like Google and Apple phones, they have real-time on-device translation. Grammarly has on-device grammar correction, and there is this project with Samsung, and there would be additional presentations soon about it. But it's example where we have sequence to sequence running with quality equal to what we can get in cloud, but in very small envelope. What about more complex tasks where we will have an on-device system that can securely and quickly chat with you about any animal or like entertain your kid and provide information about it? No, we are not there yet, but I strongly believe that with approaches that I mentioned, we will see it in a few years. Maybe like next AI on the phone would be completely running on the phone and would be much more powerful than Google Assistant and Siri, and doesn't really leak information about you. If we think about large language models and you work on device development, can we use them even though like they're completely out of reach to launch them on device? Yes, absolutely. We can we can use them to generate data because they're good zero-shot learners, so we can use them to bootstrap data. And also all of them are teachers. So even if you are not, if you're interested, for example, only in on-device, or if you're interested in large models, you still can be useful in propagation knowledge and information about it for developing on-device. And if I mentioned about being useful, and also I mentioned all this fantastic development on device that Grammarly currently does, I want to remind that we are a fast-growing company, one of the leaders of natural language processing in the world. So I invite everybody who is interested in these topics, who think that things that I talked in this presentation have sense, to join us, and we're really excited to see you here at Grammarly. And now we are moving to our question and answer. Victor, do you have any questions?
Yes, thanks, Max. That was a great presentation, and I really love your bandwagon at the end. So it shows where we're all going with a lot of fun and bands around. And before I move to questions from the audience, I have one question from myself. Like, what would be your best bet on when we'll have this in-pocket assistant, which will be able to work in offline mode and support conversation, similar to human?
I think that realistically, we see elements of it already. For example, I know for sure that Google Assistant already runs many queries on device. But I think that with current push for privacy and quick development of on-device capabilities, I think that definitely in a few years we will see it like more and more, and eventually it would be really common.
Nice, and this will open up a new era of actually sensitivity topics. What can you discuss with your assistant? How it should react, and shall we treat them as individuals or only as robots? And what does it mean for humanity?
Okay, yeah, this is a big topic. I think that people already currently afraid to reset their phones because they don't know how to bring all information that is collected inside these devices back, right?
Right. We have a few questions from the audience, and so feel free to submit your questions in Q&A tool. Feel free to use any language that you prefer. One question was about large models. So currently, large models struggle with mathematical common sense and logical reasoning problems. And it looks like that scaling doesn't help really well on these tasks. For example, latest Gopher model from Google is a good example. When they actually like generate text quite good, but struggles with simple math questions. Mm-hmm. So what's your thought about the progress on these tasks?
Yeah, there are like, obviously, there are like two questions here, right? Like one question is philosophical. Can we like continue this direction of like just scaling up these models, and this problem would be eventually solved? And philosophical answer, I think, is yes, simply because, again, like we can use as a reference Google Brain that doesn't have a special mathematical unit, but we can like multiply and other things, right? So eventually it is possible that these models would be able to like solve this. But bigger question, and more important as an engineer question, if this is something that can be really quickly resolved by simply means. And the modern approach to resolve this problem is practically to teach these models as a part of their prediction to use another tools, right? Like, for example, use calculator practically, and solve these problems this way. And if you have a well-defined problem, for example, if you want to create the system that solves mathematical problems, it can work. I think that we will see very soon systems that apply this approach. For example, if you want to build a system that help mathematical students to study math, we will see that it would be connected with calculator to solve this problem. So from engineering point of view, I think that this is something that we will see, although it a bit like breaks this nice picture of just scaling up. Yeah, so we can talk a bit more about, because it's also related to problems related to hallucination and understanding of out of world by the systems, right? What they understand, what they don't understand. But this is a big topic. But engineering solutions is pretty straightforward.
Thanks, Max. And we'll talk about this a bit in networking room. So hopefully that will be the right room for off topic. And another question for particular on device, like what do we use in Grammarly internally to deploy models to mobile devices? What frameworks and libraries do we use? And are there any alternatives that we can recommend for the people to try out?
Mm-hmm. Okay, yeah, I can say a few words about Grammarly. So in Grammarly, the main platform that we use on devices on NX, open neural network exchange project, which is an open source project. I think that it's reasonably good. It has a good integration with PyTorch, with TensorFlow. Again, a bit returning back, like at Google, I worked a lot on TensorFlow Lite, and I submitted some changes in this framework. I think that practically at this moment of time, there are many differences. There is no one platform which is the best. I think that OnNX is, if you want to start, OnNX is a very safe bet. And with my personal experience, I would choose either OnNX or TensorFlow Lite.
Thanks, Max. Any recommendations for the pipeline or framework, like how to update models on device when it's when they're on air?
Yeah. So at Grammarly, we have our own internal framework that does model deployment and A/B testing and all other things to run it on device. Unfortunately, outside, like if you want to use your own thing, it's platform dependent. So Apple in iOS has like this support for building models, which are really easy to deploy. If you want to deploy your own model, it's a bit more complex. The same story on Android. There are many like available libraries that are like that are platform dependent. There is no like common easy to use solution right now.
Thanks. And probably one of the last questions. This one is actually goes back to one of the strategies how we can reduce size of models using individual experts. So what about task segmentation? In my practice, we achieve decrease of model size using user segmentations. So we understood what layers are needed for exact users.
I think that here we shouldn't talk about users. We should talk more about tasks or like areas, right, where this model works. And this is something that people, for example, there is this work from Microsoft where they try to regularize these experts to avoid like this random access to different experts doing inference. Try to block experts together. And you can think about it as an approach where there is an expert that looks for all embeddings, I don't know, which are on topics about cars, and another expert is on topic about, I don't know, airplanes and so on and so forth. Yeah, this is valid approach. It's a bit from engineering point of view, we are moving into this story of inventing more and more complex architectures in this case. But yeah, this is absolutely possible. Although it increases speed, it doesn't reduce size of the model, and it still has this non-regular like access to memories. All these problems are mitigated, but they're not completely solved. But at some moment of time, I was very excited about it. I tried to like use this correlation of experts to bring it on device, but eventually didn't work.
Thanks, Max. And a last question before we move to networking room. So do you believe that quantum computing may revolutionize the transformer training and inference? And before you answer that question, I recall that we had a summer hackathon in Grammarly, and one of the projects was actually about exploring quantum using quantum computations for neural networks. And if I recall correctly, the answer was, yeah, kind of, it will revolutionize, but probably not like in nearest decade or few decades. So I'd love we were there.
Okay.
Max, over to you. Like, what do you think about it?
I do have some training in quantum physics, but it was in the 80s, but I still try to keep up to date and read about it. But I'm not a specialist in quantum computing by any stretch of imagination. But what I think is that transformers, when I talked about them, they're perfect architecture and they like very popular nowadays because they're a great match for the hardware, right? So they are fast because they're parallel and our hardware is parallel, and this is the story. If you move to quantum computer, which is different hardware, which actually is good in solving different kinds of problems, right? Like nobody even planned currently to build a quantum computer that can do matrix multiplication. I think that it won't work. It's just not what this computer is designed for. Therefore, I don't think that quantum computers and transformers can be connected, and it's a nice way to move forward. At the same time, we can think about quantum computers as a different approach to computation, about different framework. It's just different view on this. You can think about like electronic computers and mechanical computers. As somebody asked, like, do you think that new electronic computers would be a good way to faster implement this arithmometer like wheel? No, it's not, because there are no, like nobody really model arithmometer wheels in electronic computer. The same thing is here. Maybe it will be breakthrough in language. We won't see it in a short future because of capacity of these devices. And I think that when we will see it, it will be very, very different architectures that we currently use.
Thanks, Max. So with that note, looking into future, I guess we can move to networking room. Vika will post a link to the chat. Please take a moment to ask any questions that we haven't answered during this Q&A session directly to Max in the separate Zoom room. So there is a link in the chat. Please join and take a moment to ask anything that you want to know about natural language processing or natural language understanding. See you there in a second.